Getting it?
Yeah, now it has reduced a lot.
Okay. Just a fan noise. Fine. Okay. Good. So we are recording also. We're live. Fine. So we'll begin today's session. I'll, I'll come to the week 7 live session for your course Intro to Machine Learning. So today we'll do one thing. We'll finish up the pending discussion on reproducibility. So we had that point pending from the previous week, and also we'll do one question from the week 6 quiz, and then we'll discuss some advanced topics on neural networks. In case you want to discuss, you have any doubts on decision trees, the quiz that you guys did on week 6, we can take that up. Otherwise, we'll continue with the discussion on the advanced neural networks. Okay. Good. Okay. And yeah, so as usual, whatever has been recorded, is spoken will be recorded, and all this will be made available in the PDF format. And just as a reminder, the assignment solutions have been posted. So for all weeks, you can check actually in your in the course web page. You will see that it's been posted by the NPTEL folks. All right. So last,
Hello, sir.
yeah.
Sir, I want to ask about our exams. So when we get any our information of center and everything.
Oh, actually, I'm not sure, how that is being handled. The course TAs might be able to, help you
So
understand
it's
that.
normally between from the exam date to 2 weeks before exam date. When it happened there.
Okay, so 2 weeks before exam date is what you're saying, Shashi, is it?
Yeah.
Okay. Huh,
Yeah.
Okay.
yeah, so that would be the thing. And in case you want some more, clarification on this, better to ask on the discussion forum. And so the course TAs might be able to, help you help you clarify those doubts at least.
So, sir, for exam purpose, we have to do only assignments and quiz questions, or anything else we can expect from.
So anything else in the sense, so yeah, but yeah, so whatever has been taught in the course will be asked. More importantly, like programming questions, mostly they won't ask, because that is taught as a separate, part of the course as such. The 3 sessions that you guys have, right, on Tuesday and Saturdays. But otherwise, I think the course material which have been taught by sir, and the assignments and the practice questions, all of those are, fair game for your exam. Yeah. Okay, fine then. We'll move ahead if no other questions. Okay, so we wanted to talk about, like, work should be reproducible. So I give a brief inkling of, what reproducibility means. So let's say a person A, he has done his some. Oh, just give me a minute. There seems to be some issue. Okay, fine. I think it should be fine now. Okay. Okay. So we have a person, let's say A. Now he, did some work on some machine learning algorithm, and so therefore he has some data, right, and some code. So okay, fine. Hmm? Data and code. Okay, fine. This is okay. Fine. Some data and code he uses to, publish some results. This person B uses the same data and same code, but gets different results as such, right? So they don't match, right? Now this what has happened is in the recent years this has happened a lot with people, right? So there is some published result which other people are not able to reproduce on their machines, or on their code and their data sets. So the idea is that if your work is reproducible, then it breeds trust in your systems, right? So trust in all of your mechanisms that you have done. It may be your pre-processing pipeline, it could be your modeling approaches, right? And many other things which go into making a ML model successful, right? If it doesn't work out, like if it is not reproducible, then what happens is, let's say the inferences whatever you obtain from your ML model, they all are in the shadow of doubt, right? So therefore making a work reproducible should be one of the priorities of any ML scientist. So with that in mind, some steps that you could do to make your work reproducible. One thing is using seeds for your random number generators, right? So as you guys know, like there is no purely random number generator in using machines, right? All we have is some pseudo random generator. So basically setting seeds on any of these generators actually controls the order in which you get the random numbers, right? And hence using seeds and sharing this seed with the other person, with the community at large, tells them that okay, this is what I used, and therefore whatever results I've got is conditioned on using these seeds, right? So in case somebody uses a different seed and still finds a result, which is a good thing, and if it doesn't find the result, then it's open for debate, right? That is point number one. Point number two is that the exact procedure for training, right? So for example, it's possible that you took, let's say, 80% of the data for training, right? But which 80%, right? And how did you get this 80% from your data? Did you take sequentially 80%, or you took it at random from the from some like sampling procedure, right? So all of this can matter in the way the result was obtained. So hence it becomes important to share all of these procedures with the community at large. Okay, that's the second thing. Third thing is share your whole code itself if possible. Now this is not it it may not be possible always, because for example, let's say if there is some proprietary issues, then we can have some issues regarding can we share some code or not. But if there are no such issues, I would always tell you to share your code, because then it lets the other person know that if you run this code on this data, this should work for your inferences, right? That is the third thing. Fourth thing is like we also have different machines in the market, right? For example, let's say you ran your code on some 9020 TX GPU or something, right? So sharing all of this also helps them understand that in case that there was some difference in the way the batch was being processed, right? So all of that can also be controlled for when you share this kind of details. And we also have library versions, right? For example, let's say there was some bug fix between the PyTorch 1.8.1 to 1.9 version, right? So if you're using 1.9, you might get a different different result compared to 1.8.1, right? So it's basically like keeping a track of all of these library versions, machine details, and sharing the codes and your seeds and everything makes your code a bit more makes your result a bit more reproducible, and therefore can help people to get inferences from your data. Okay, So this is about reproducibility, and now we'll go to the one question which I found like good to solve in the in the quiz of week 6. The last question where we had, for example, let's say a data set with only one attribute which is categorical. Suppose that there are q unordered values in this attribute, right? So how many possible combinations are needed to find the best splitting point for building the decision tree classifier? Okay, so any ideas how you would go about solving this problem? Any ideas?
Hello.
Yeah, hello, tell me.
Yeah, you can go about enumerating all possible ways of splitting this since these are categorical attributes. So what you do, you can encode your possibility like suppose you have three colors R, G, and D as Sir explained. So if you are selecting R, you encode that as 0. Okay. If you select green, then you encode that as 1. And if you select blue, then you encode that. If you do not select blue, then you encode that as 0. So you can see that every selection, if there is a bijection between the three-digit binary bit strings and the number of selections you can have. So in suppose there are q bit strings, then there are 2 to the power q minus 1 combinations, right? But we do not consider the combinations that has all zeros or all ones, means all selections, all either selected or all left out. So the final result gives 2 to the q minus 1 minus 1. So that is how I came up with this thing.
Okay, yeah, good. So it's possibly one way of doing it. So help me understand, you said 2 power q minus 1 possible bit strings, is it? Why?
Yeah, because there is a symmetry issue, because 101 is same as 010, right? So if you divide by 2, so that gives 2 to the power q minus 1. And you then leave out the all selections, all selected or all not selected. Only one combination is there for that.
So you said 100 and 010 is symmetric. Is that what you?
Yeah. These are basically the same selections, right?
No, because this is just choosing red as one. This one. This is green plus blue. This is green and red plus blue, right? In one group. These are not same, no?
Yeah, that is there. But once is that. No, 010, I'm telling as 011. The complement of that.
Yeah.
Complement.
The complement.
That I am not counting, because one
Correct.
you select one, that automatically means you have taken care of the other, right?
Right. Correct. So yeah. So this is the right approach. So you can take it. So this again still red and green plus blue in one group and red in another group. So therefore these two are same. Same in some sense bins in some sense, right?
You have to avoid this double counting thing.
Double counting, right? So basically, okay, good. So we have, for example, let's say two bins. It's two groups, for example. Okay, group 1 and group 2. Okay. So what you want to do is you want to fill this group 1. Okay, and automatically whatever is not been put in this group 1 bin, you put it in the group 2 bin, right? So basically you're going to choose whatever. So let's say you have q possible values, right? So you will choose some number of values from this q. You'll put it here, and the remaining would go here, right? Now how many possible things that you could choose from q is basically 2 power q, right? 2 power q is all possible things, that possible number of subsets that I can choose from q possible values, right? So once I fill whatever is there in this g1, the remaining will go into g2, which is fine. But now the issue is that the two combinations, the two sets, which is basically phi and all, are not valid, right? Because I want at least one in both of these groups, right? So -2 I will do. That is for choosing so making sure that each of them have at least one element in them, right? And I need to do by 2 because of the fact that this group 1 and group 2 is basically an arbitrary sort of a number assignment, right? So if for example I put A and BC here, among for example A, B, C are my three numbers, then I can putting this as B, C and A is the same, right? So for every of these group assignment, there's another group assignment which is actually just the same, but we have the group number being changed, right? So since we don't have any um, uh, hard requirement on which group number should a particular subset go to, so I can do by 2 here, and this would just lead to 2 power q minus 1 minus 1. Okay, so good. So these two are the approaches to think about. So one is looking at them as binary strings and trying to see that the complements are actually the same group assignments, so therefore you will divide by 2, and the same thing is here. Okay, any doubts here, anyone? No? Okay. So we'll do some
Raj, excuse me, Raj.
yeah.
I had a small doubt regarding one of the questions in the assignment.
Okay.
So there was a problem that had many. I do not remember the exactly quiz number. So I selected an option as the decision tree is a high performing, but it was incorrect. So I got that problem incorrect. Okay, just hold on for a sec. So it was, I'll just read out to you the question. Which of the following is our major advantages of decision trees over other supervised learning techniques? Okay. So I had selected as an option higher performance, but it was incorrect. So I got the question wrong. So my question is, Professor actually while introducing decision trees said that decision trees are very, very much suitable for certain class of problems. So I thought that high performance may be a good option to select. So am I wrong in my thinking? Correct me if I'm wrong there.
So I mean, higher performance is very subjective, no? Because it's possible that there are problems where it does well, but and in some problems it may not do well, right?
Yeah.
And actually speaking, because decision trees are very unstable sort of algorithm, I don't think high performance is their strong suit in some sense. Right, because just a small tweak in the data will just give you a different model altogether. So again, that's what I understand as the rationale for not choosing high performance. But if you want more detail on that, we can ask the course TS to shed a bit more light on this.
The discussion forums, right?
In the discussion forum, yeah.
So what I understand from your discussion is that it's not uniform across the board.
Correct.
Or maybe some problems, class of problems, it is good, but not across the board. So that is the main issue, right?
Yep. Yeah. Correct.
Okay. Got it.
Yeah.
Thank you. Yeah.
Okay. Good. Fine. So we'll talk about something called as the parameter tying or sharing sort of an approach in neural networks generally. So in I think sir mentioned something called this parameter tying approach somewhere in the ANN lectures. So I'll just go through a bit on how this has helped the community at large in doing something like this, right? So one idea or one motivation of this parameter tying approach comes from the fact that let's say when you have a lot of parameters, okay, so we have for example something like this, right? Some neural network like this, right? So it's as the data grows in its features, the number of parameters which we use to represent in a neural network will also grow large, will grow proportionally, right? So hence so one thing which people thought about was that, let's say if we can force that some of the weights be same across different input points. So for example, let's say there is three, for example, three input neural network, right? Now what I'm doing is I'll say that, okay, this weight and this weight is is the same, right? So instead of using W1, W2, W3, I will not use W3, I will use the same weight W1 here. Okay. And so basically what happens is your your whole issue of overfitting, which was because that you had like a very high dimensional space in which your ML algorithm can basically learn the training data altogether, right? It can learn the training data because of the fact that it is high dimensional, more dimensional compared to your dimension of the data, right? So in some way we are making this high dimensional input, high dimensional space of your weight space to some low dimensional space, right? By tying up the weights, by sharing the weights across different input dimensions, right? So it becomes a bit less dimension space, right? And so hopefully we might not be overfitting, so overfitting issue may be reduced, right? So this idea becomes very important, I mean became central when they spoke about something called as CNNs, right? In CNNs the idea is that, let's say you have an image. Okay, so CNN stands for convolutional neural network, convolutional neural network, right? So which are mainly used on images, right? They became famous when they started working on images and giving good results here. Okay, so the idea is that so let's say you have like a 32 cross 32 image that you have in space with you. Okay, so for example, let's say we currently work with just one channel, so it's like, for example, like a monochromatic image, right? Some grayscale image. Okay, so all your values here are some number between 0 into 55, right? Now the idea is that you will have a weight matrix. Okay, a weight matrix, also called as kernel, right? This kernel is different from the kernel that we saw in SVMs, by the way. So let's say I will use a 3 cross 3 weight matrix, right? So what I do here in this CNN is that I place this weight matrix on this on this, let's say, image here, right? So whatever 3 cross 3 was present here, okay, so I then multiply each of the elements present in this input with the weight here. Okay, get the summation across all of these values, and that is my output value, right, from this operation, right? So what I do is I get like summation wi xi, where this I is basically going from this 1 to 3 and 1 to 3. So 1 2 3, let's say j, right? Okay, so then what I do is I shift this kernel, this weight, one step towards the right. Okay, one step towards the right, and then continue this multiplication process again. Okay, with the next elements in the input, right? So now what will happen is I will again have wij x, let's say I comma j plus 1. So again ij in 1 to 3. Okay, this is some input output, this is some output, right? So what is happening is, in case if you want to do this using your normal neural networks, right? So what would happen is that you will have one weight per input dimension, right? So what will happen is, for example, I have 32 across 32, so I'll have like 1024 weights, on this image, and I will try to learn these 1024 weights. Here what I'm saying is I'm saying, okay, I will not learn 1204 weights. I will learn just 9 weights, 3 into 3, 9 weights I will learn. Okay, and the way these 9 weights are used is by this shifting and sliding sort of a procedure, right? So you keep on moving your weight matrix from one row to the from one column to the end, and from one row to the end of the rows, right? And then get the outputs in this format, and use that to basically generate your loss functions, right? I mean uh, weight output, right? So in this case, what will happen is, when you're trying to update a weight, so for example, let's say dou e by some dou, so the error, let's say, or loss, yeah. So what you'll do is dou L by dou Wij. When you try to do, what will happen is, you will have all of these elements coming into picture, right? Because Wij is affecting the output with all of the input that you have in place. Okay, so this particular differential will have almost the whole image, I mean the whole input as part of the uh, update equation, right? Because each of these Wij is affecting the output of output against each of the input elements, right? So all input dimensions will be used here, right? Okay, so now so basically what has happened here is, you are sharing a particular weight, that is this Wij was shared between Xij, was shared with between Xij plus 1, and then so on up till the whole particular image, right? So this is the idea of parameter time or parameter sharing. Okay, this is a very powerful idea in some sense. And what they saw, so what are we saying, right? By this, what are we saying is that we are saying that, okay, this weight matrix basically tells you to capture something which is invariant in the space of your image, right? Capture something invariant in the image space, right? So what they did then was to look at the outputs of this this CNNs at different layers of their network, and basically for faces, what they saw was that the initial layers captured something like the edges of your face, for example, the eyebrow, or your nose, and so on. Then the later layers, for example, the initial layers, when you have the image here, the so as you basically go higher, deeper and deeper in your neural network, they're capturing more and more complex items. For example, here they're capturing like parts of face, right? For example, an eye, or nose, and so on, right? And then at the end, basically they're able to recognize a particular image is a face or not, right? Then they say, okay, it's a face or not, sort of a classifier. Okay, so the way to update these these parameter shared sort of neural networks would be to look at, when you have the differential, what will happen is, all the input dimensions in which this particular weight contributed something would come as part of your loss update equations, which in a way makes sense, right? Because you're trying to look at something which is invariant between these two dimensions in place. Okay, that is the idea in convolutional neural networks. Now in RNNs, a similar idea was used. So for example, let's say I have in RNNs, okay, what I do is, I'm saying, let's say I have a sequence of data present with me, right? So let's say I have x1, x2, x3. Okay, what I do is, I say take this x1 and multiply with some weight, let's say wx1, right? Whatever output you get, I will use that in some way, and I will use the same weight, say same weight matrix w, and I'll apply this on the x2 also. Okay, and I will apply this w on x3 also. right? So what will happen is each of these elements in this weight matrix, when you differentiate with this loss function, whatever loss function you have, will basically have inputs will basically get updated through time, right? So we are saying that, okay, look at the effect this weight had on the third input in sequence, on the second input in sequence, and on the first input in the sequence, right? So this will basically get updated through the time, right? So it'll look at the whole sequence, it'll look at the whole sequence of inputs that you put in your recurrent neural network. Okay, so it's called recurrent because what is happening in some sense is that it's using the previous output of your previous state, let's say ht minus 1 and xt, and it will use this it will use a shared parameter space for computing between on time t, let some w, and it'll output h of ht, like some output from the particular layer. Okay, and this ht will feed into the next layer with the same parameter space, which is being kept common across different time steps. Okay, so this is the idea of parameter sharing, and how it has helped advance ml in a lot of sense, right? So so it's parameter sharing. The idea is that because you have a high dimensional space in of your weights, what this helps is to make it a bit less dimensional in and therefore hope that we will not overfit on the data. Okay, that's the idea. Any doubts in this currently? Any other clarifications you want?
Raj,
Yeah.
yeah, in CNN, I believe that the filter of the kernel which you are applying tries to preserve the translational symmetries of the system, right, of the image.
Right. Yeah.
So, so will it try to capture the rotational symmetries?
Rotational symmetries. I don't
I was
think
just
so.
thinking.
I don't think so, actually. Yeah, no. So for that, the way you build a kernel will have to be changed, and also I think the way you impose the kernel on your image as such, right? Because of the way you're doing it in this format, right? I don't
Yes,
think
yes.
it'll be able to capture that. But again, like I would think about it, and hopefully there are people who have tried doing that. So we can see once what is the approach that they take to make sure that they capture this sort of approach also.
Yes, yes. I think that would lead us to the domain of graph convolutional neural networks, I believe, for capturing other symmetries of the system.
Graph convolution.
GCNN.
Graph convolution, yeah. So there you need to have this order invariant sort of approach,
Yes.
where any of the nodes can regardless of the position of the nodes, can affect your current node,
Yes.
right?
Yes.
So yeah, that may be. I do see that there is some resemblance, but exactly how will that work out is not very clear right now. Yeah.
Yeah, but if you can just find somewhere how they will capture the rotational symmetries and can probably discuss next class. So it will be very interesting.
Okay, sure. Yeah, we'll see. How if I can do that. Next class actually will be a bit more on how to have how to think how to you use metrics for evaluation. So yeah, so we'll see.
Okay.
How if we can bring that here, we'll see. Anyway.
Okay.
Yeah.
No issues. Thanks.
Okay, so it's basically one idea which I want to discuss with respect to advanced neural networks. The other idea was that this idea of modeling probability distributions as neural networks, right? Now this was a bit of a shock for for me also when I started seeing something like this. So the idea is the following, right? For example, let's say you want to generate a new face, right? From by learning about all the faces that you have in the world, right? Now what will CNN give you, right? CNN will just, the way CNNs are trained is that you have some sort of a supervised, loss to be learned, and the idea is that you have some task to be done on that image. For example, let's say, is the image of a horse or a donkey, sort of a thing, right? So one thing that we know is CNNs are able to capture good amount of, they work very well with images. They're able to capture things that we as humans in some sense capture in our brains, right? Now the question was that, can we use something like this to generate a new image, right? For example, having seen all the faces in the world, can I generate a new face, right? Because in some sense this would be the, the holy grail sort of a metric to test a neural network, right? So if it has actually learned what makes an image, right? All the positions of your eyes, and the things that you should have two eyes, we should have the eyes above the nose, and I have that structure in the image, right? So if the neural network has learned reasonably well about the structure, so it should have no problem in generating a new image, a new face as such, right? Which has all these properties properly made. So this idea of generation is basically just sampling, right? So that is basically, let's say you have some probability distribution, which I guess you guys already know it is a p of x. That's your data distribution, right? So can I learn this distribution itself, right? In some possible way. For example, let's say I approximate this distribution using some q of x or whatever, right? Now so now, because I have this q of x as a distribution, what I can do is I can basically keep sampling from this distribution, right, to generate hopefully a new face, right? Because if this p of x is all the faces distribution, let's say all the faces in the world, right? So by learning the distribution of this faces, right, if I'm able to sample from this distribution, so I should get a new or some old face, right? Old in the sense known face, right? So with this question in mind, the problem becomes a bit more challenging, and the thing is that now we want to learn a probability distribution altogether, right? A probability distribution. Now there are multiple approaches which exist in the world, but one idea that I want you to think about is this. Let's say, okay, so how do you learn a distribution, right? So what would you need in some sense to quantify a distribution, right? Now in case it's a parametric form. For example, let's say I say it's some Gaussian, right? So Gaussian of mu comma sigma, right? Okay, let's work with multidimensional data. So I'll have some covariance matrix, right? So if I say you that I have this distribution as a Gaussian, so then what would learning a distribution mean? Would just mean learning these mu and sigma, right? So if I can get this mu and sigma, learn this properly, then I actually have the distribution which the actual is, and therefore sample from this particular distribution, right? In case there is no parametric form for the distribution, right? So like we have some other approaches. For example, using Gaussian mixture models. You will come to this in your upcoming lectures, but then, like, so let's say if I don't have a parametric form, then what do I do, right? So the current approach in some sense in the literature is that you basically approximate it with some known distribution. So for example, let's say your px is some data distribution, right? Is some data distribution. So now what do is you say that I have p theta, which is some model distribution, right? and based on whatever model you choose, you try to approximate this with this, and you say okay, p theta and px should be as close as possible in some way. You measure using some metrics, right? So what you end up doing is that you say okay, I will learn these parameters theta of this model distribution, right? So one way to do that, right, one way to do that is something like this, right? So let's say I want to learn a newcomer sigma. Okay, this means that I need to learn mu and sigma. So what I do is I have a neural network like this, okay, which takes in some input, right, some input, and what it does is it doesn't output the distribution as such, it outputs the mu and sigmas of this distribution, right? Now I use this mu and sigma in my code or whatever, right? And then I sample from the code saying that okay, take this mu, whatever I obtain. So for example, let's say xi was the input, so this mu now becomes a function of the input, mu of xi, sigma of xi, right? And what I say is okay, now sample from this mu of sigma xi and this one. So have these mean and variance with me. So I can basically sample from now I can sample from this n, right? The Gaussian distribution, right? So this is one way of doing this sampling from a neural network, right? So what you do is you get this mu and sigma. Sorry, you get this sample. For example, let's say some zi. Okay, now you have another neural network which takes in the zi and produces your some xi hat, right? Okay, so now given this mu and sigma, what you do is this xi will basically be the image that you want to generate, right? Some face, for example, right? So while training, what you will do, you'll say okay, I have this some face face one, this try to generate this face one again. Okay, so what you'll do is you say you learn this mapping properly, learn this mapping from face to the input, face to this mu and sigma, so that I can sample correctly. This zi should be sampled correctly, and then once you have this zi, you try to map this zi to your xi, and generate a face. So then what you will do is you'll say okay, once you have trained this network, what I will do is I'll keep on giving different zis here, right? So I'll sample this zi from some distribution again, from whatever I want to from where I can sample. So when I keep generating these zis, this neural network which maps this z's to x's, okay, now takes as input some z and maps it to some face, right? So in this way, just by having a neural some sampling distribution, I can actually generate faces from this faces from a neural network, right? It's a very clean and very interesting idea, right? To generate different faces, what you do is you just keep on sampling different z's from this distribution, right? And pass it through a neural network, right? Which takes your z to x space. Okay, this is one idea. The other idea which is there in the currently in your research is this. So so do you know that there is there's a one way to generate so let's say I have a random variable x, which is some uniform distribution between 0 and 1, let's say between 0 and 1. Okay, now I can actually have a function, some f, which takes x to y, right? And the function of this random variable, that is f of x, this y, I can choose this function in such a way that y becomes a normal Gaussian distributed function variable. Okay, so choosing this f is in your hands, right? So what you can do is you can basically transform some random variable to another random variable of interest. For example, let's say I want a Gaussian distribution from uniform distribution. What I do is, if I can learn this function f, which actually exists in the world, right? So basically, what you can do is you sample any element xi from this u of 0 1, right? You pass this through to a function f, right? It generates yi, and the way this yi would be in this n01 sort of a space, right? So with this idea, what people thought was that, let's say I have some input z, right, which is, let's say, normal distributed. Let's say I will use n01 for some in some sense, right? And I have this px, right? Px is what? Px is some data distribution, right? So what I'm trying to do is, right, I'm trying to learn this function f, right? If I pass z to it, right, it should give me some x, which is which basically follows the data distribution, that is px, right? So the way to do this is you get this z, from sampling from this n01, you pass it through a neural network, okay, which then produces some x, which hopefully is from this px distribution, right? So this idea is uses something called as GANs, generative adversarial networks. So the way to train this network, the way to learn this function fw now it become, right, because it is some parameterized function which you have with you. So so how to learn these parameters is through some you have another network which will help you understand, okay, is this x the right x or not, right? And once you have trained this network, that is, once you have learned this function fw of z, what you do is you keep on sampling from n01, you keep on getting x's, right? So basically keep changing this z space, the input of the to this neural network. You keep on getting new faces from this neural network, right? That's the another idea which I want to think about and appreciate, which is this learning a probability distribution using neural network, right? So any other thoughts here? Any questions, ideas? No? Okay, fine. So it's it's all I had for today. So next week, what we will do is we will look at evaluation measures, right? In this, we'll actually spend some time trying to understand this class imbalance problem, which is a very prevalent problem in some sense, and we'll look at measures through which you can solve this class imbalance in both regression problems and classification problems, right? And yeah, so that will be the idea for the next session. So any doubts now? Otherwise, we can close the session.
Hello, sir.
Yeah.
So in the evaluation measure, sir, in the next week, sir, I want to know that like accuracy is there, precision is there, recall is there, specificity is there. So I want to know which will be more suitable for which field. For example, medical field is there. So which we can apply that, which will be way more suitable like that. So I want to know just a basic thing I want to know about that.
Okay, sure, yeah. So we'll cover that as a part of this classification, this one, right? So we'll talk about accuracy, precision, recall. We also have something called as F1 scores, and then there's the way to make it even more general is F beta scores and stuff like that, right?
Yes,
So
sir. So the application where we are going to use that one like that.
sure. We'll I'll get some examples on to where each of these measures may be more and more useful. Would that
Okay.
work?
Okay, sir.
Yeah. Okay. Okay, good. So
Raj,
yeah,
just a small question.
yeah,
So you mentioned two examples of generating images or whatever data you want.
Hmm.
So the second was GAN. The first one was autoencoders, I believe, right? A variational autoencoder part, right?
correct.
The
Yeah.
first one.
Hmm.
Yeah. So just thought you did not mention that, so I just wanted a clarification on that. That's
Yeah, yeah, yeah. So the first one
and
was yeah,
and
variance.
then and then also for after generating an image, you have to compare it to probability distribution. So you have some measures like Kullback Leibler divergence and all those stuff, right?
Correct. Yes. So
Contrastive divergency and all those.
correct. Huh. So the idea is that when you want to train this network, when you want to learn these, the weights here and here, for example, what you do is you basically have this KL divergence metric, which helps you understand, whether the two distributions are the same or not. That is one. And in GANs, we actually have a lot of thing going on in GANs. So in GANs, initially what they started was they said, okay, we'll use KL divergence. They found some issue, problems with this metric. They shifted to something called as F divergences, right?
Okay.
Which is basically like a general form of KL divergence. And then we have another thing which came up, which is called the Wasserstein distance, right?
Wasserstein distance, right?
Distance.
Wasserstein, yeah.
Wasserstein distance.
Okay.
So this is also
Yeah,
called
yeah,
as
yeah.
Earth mover distance, EMD.
Earth mover distance. And
Yeah.
the F divergence, I believe, is the Frechet, right?
Sorry?
Frechet divergence, right? F divergence.
Is
F divergence.
F divergence is what you're saying?
No, I think the F is an acronym for something like Frechet divergence or something. I do not know exactly.
Oh, is it? No. So I'm not sure. So the way the way this function is basically something like an integral over I think q of z, some f of p by q of z. Yeah. Right.
Okay.
Huh.
So these are all the
where
metrics for comparing probability distributions, right?
Correct. Yes. So because you need some way to understand whether your px and p theta, that's your model distribution and your actual distribution, how close or how similar they are, right? So
Yes.
we need some measure which works on this probability distribution space itself in the first place. So
Yeah.
so the scale and your F divergences, your EMD distance, all of these are basically working on probability distributions. Yeah.
Oh,
Yeah.
thanks.
Okay. Okay, good. So we'll stop here. This is a good stopping point. So we'll see you guys in the next Saturday class. Okay. Thank you.
Thanks.